for inviting me, and it's really great to be in this session actually, because to quite some extent my talk connects to the previous two talks, as you will see in a moment. So this is joint work between with these colleagues, Alexei Chechkin, an expert on anomalous stochastic processes. Peter Dieterich did the main part on the experiments I'm going to mention to the end, and Friedrich Lenz is a former PhD student of mine. So, a brief outline. First, well, you've already heard about that on quite some occasions, fluctuation relations or fluctuation theorems. Mark Pollicott has briefly mentioned them, Matteo has just mentioned them, you as well. So I will again briefly outline them to you. And then, well, also this has been done before, I will discuss again Langevin dynamics. So first, we'll just as a motivation show you of how to prove fluctuation relation for ordinary Langevin dynamics as a warm-up. And what I'm mainly interested in is if you make Langevin dynamics more complicated in terms of a generalized Langevin equation, again it was in your talk, with specific memory kernels, and then I would like to check again what happens to fluctuation relations. So in a way it's really complementary to what you've been talking about. And this generalized Langevin dynamics is nothing else than what one could call correlated Gaussian stochastic dynamics. And to the end, in order to somehow indicate that this is just not some theoretical playing around, but may have practical relevance, I would like to discuss two examples where one already has seen similar results, namely glassy dynamics and what we are currently doing, cell migration. Although cell migration is not really Earth science, well, at least cells are living on Earth, that's it is an experiment where we see something going on. And I would be happy if anyone has any ideas where within the Earth sciences something similar might be observable. Okay, let's start from the very beginning. Again, you have heard about that before to quite some extent. Let's consider a classical particle system that evolves from some given initial state into a non-equilibrium steady state. And we can then wish to measure the probability distribution here, rho of xeta t of entropy production, xeta t during time t. And then, as you have seen before already, what people showed over the past 20 years was that this general large deviation form holds for the ratio of entropy production. So if you look at the logarithm of the probability density to obtain positive entropy production divided by the probability density for the negative entropy production, then you find that this logarithmic ratio is equal to the entropy production along the trajectory. And this is an example of a fluctuation relation. In fact, here I'm speaking, talking about the transient fluctuation relation, because I'm not starting in a steady state. I'm starting at a given initial state and then look at the system of how it evolves into a steady state. And as was already mentioned, well, these things came up about 20 years ago by Evans, Cohen, and Morris, who did computer simulations for shear fluid in non-equilibrium, and also then was put onto safe mathematical grounds by Galavotti and Cohen in form of a rigorous proof. Both of them actually have, strictly speaking, considered the steady state fluctuation relation, but here I'm really interested in the transient form. And that was done later on. And why are they important? Well, they are of very general validity. In fact, their existence has been proven for many, many different systems under very general conditions. And they seem to be one of the rare principles that are valid even very far from non-equilibrium. They generalize the second law to systems in non-equilibrium, and in particular to small systems. You do not need to be in the thermodynamic limit, and that's why many people got so interested in them. Connection with fluctuation dissipation relations. We have already heard about that to some extent, and in fact, that's exactly what I will also elaborate upon, but from a different angle. And they can be checked in experiments. A famous one was about 10 years ago by the Evans group. So what they did was just they followed a particle immersed in a fluid, and within a harmonic potential, they dragged the particle through the fluid, measured the work fluctuations, and then verified the work fluctuation relation for this particle experimentally. And one might say that starting from about this time, then there was really a boom in this field, and studying fluctuation relations became very, very popular. While over the first 10 years, not too many people noticed that this is an important concept. Okay, very brief outline how the fluctuation relations are related to the second law. So a very naive argument. What you're interested in is the probability distribution function of the entropy production here, and it may be some function like that evolves in time, T1, T2, T3. So for example, if you have a particle on which an external field acts, it spreads out, diffuses, but also moves in a direction, like here. And then simply apply the fluctuation relation, let's assume it's valid. Then you solve for rho of xeta t, which is this. So that means that the probability of positive entropy production is equal to the probability of the negative entropy production times this exponential factor. But then it's trivial to see that, well, then obviously this is greater than or equal to the probability of the negative entropy production. And then if you multiply with xeta, integrate, then immediately you get the second law, so that the average is greater or equal to 0. Okay, this slide actually is my attempt of justifying my presence in a way here at this workshop, and also my presence here at the Newton Institute, because some people call the Langevin equation Newton's law of stochastic physics. Well, it's just Newton's second law, but not for a deterministic force, but also by incorporating a stochastic forcing for a particle immersed in a fluid. And in fact, what I learned from Nick Watkins was that some people use that to model the dynamics of the Earth's surface temperature as follows. Namely, Ripdahl came up with this linearized energy balance equation derived in this way. So T is the temperature. So on the left-hand side, you have the time derivative of the temperature. C is the heat capacity. The first term, in fact, is the kind of friction, which he has derived as a linearization from the Stefan Boltzmann law. Where S equilibrium, he called the equilibrium climate sensitivity. F is the solar radiative influx, so the field. And then we have the stochastic forcing, stochastic perturbation. Don't ask me details about the justification. I'm afraid I'm no geophysicist, but at least that's what you can find in this paper. That's all what I can say.
Maybe you know this. He's rediscovered in some physics journal. This thing goes back to the mid-70s.
Yeah, sorry.
I'm not surprised.
In the climate literature.
Yeah. Michael, I think that the Ripdahl paper is going to do what you're just going to see in a sec. It's not claiming to have invented, you know.
Well, but he has derived it in this paper actually here, 2012, in the appendix. In fact, not sure whether there was a citation to this earlier work, but I certainly am not surprised. I mean, that this has been around for ages.
It's like saying there is something called H with a bar and it has an important value. It's like, yeah, it's a...
Okay, but in fact, so there are two papers. So there's a preprint here, where in fact the idea was to generalize that by incorporating memory. But in fact, in this paper, if you look at the appendix, then indeed there's a derivation of this equation in there. Not sure to which extent he was aware of previous literature. But again, I'm just citing literature here, no claims from my side. Okay. Yep. Okay. So this is the motivation that apparently Langevin dynamics is important for Earth science. That's the only point I want to make here. And I'm happy to learn more here. That's why I'm here, to learn more about crosslinks. Okay, warm-up fluctuation relation for Langevin dynamics, very easy exercise. Now we consider the overdamped Langevin equation like here. So we do not, we assume that acceleration is negligible. We just focused on the overdamped one. Now for a particle at position x under a constant field with noise. And I just set all irrelevant constants to 1. I just keep the strength of the field as a parameter. And in fact, for this Langevin dynamics, the entropy production is equal to the mechanical work because we have no fancy potentials. So it's just, you just need to multiply the position by the field. But that means that for the PDF, you have a very simple scaling. That means the system is so simple. Once you know the position PDF, you know the work PDF by a simple scaling. So it remains to solve the corresponding Fokker-Planck equation for a given initial condition. And here, for a certain reason, I take as an initial condition that the particle starts at position 0, at time 0, because for the systems I'm going to study in the following, there may not be a well-defined equilibrium density, so therefore, to be on the safe side, I always choose this initial condition. The position PDF then, well, as everyone knows, is Gaussian, and if you want to check for the fluctuation relation, then you simply look at the ratio of the PDF for positive work divided by the PDF for negative work, take the logarithm, and then you can already see what's going on. So what matters is really determined here, but what you have in the exponential. And in fact, then you immediately find, and going back to your talk, that the work transient fluctuation relation holds if you have this relation between the moments, which for this system is nothing else than the fluctuation dissipation relation of the first kind. So if you have this fluctuation dissipation relation for these systems, it's trivial to see that we have the transient fluctuation relation. And if you want to have a nice reference, there's this paper by Van Son and Cohen where, in fact, these things are summarized. And in fact, I will come back to that in a moment, because if I generalize the dynamics, that becomes more non-trivial. Now, in fact, that's what I want to do. I want to check the transient fluctuation relation for Gaussian stochastic processes defined by this generalized Langevin equation that we have seen before. Generalized in the sense that here we have a memory kernel on the left-hand side. So we integrate, the fiction is more complicated. It's not Stokes. It has a time-dependent memory kernel. And such equations have been around for a long time already by Kuber and many others. And again, we have a constant field on the right-hand side and Gaussian white noise. Well, Gaussian noise, I should be careful. That's exactly the point I want to make. So we have Gaussian noise and a memory kernel. And such dynamics can, in fact, generate anomalous diffusion, meaning that the mean square displacement does not grow linearly in time, but there's a power law, where alpha is not equal to 1 in the long time limit. And some examples of applications are polymer dynamics. So, in fact, in this case, the memory kernel has been calculated from first principles. It was not a simple power law, but I think a product of power law and exponential. And that's what I'm going to elaborate upon later on a little bit, biological cell migration. Now I want to consider two generic cases of this type of dynamics. First of all, what is called internal Gaussian noise, meaning you have a fluctuation dissipation relation of a second kind, just as you already mentioned, namely that both the memory kernel and the correlation function of the noise have the same memory kernel. And in this case, you might think, for example, of a power law, although for the internal noise here, it's not very important. So in a way, this is the same argument that you've heard about in the talk by Christian before for this type of systems. So if you solve the corresponding generalized Langevin equation in Laplace space, then you can immediately show that FDR2 implies FDR1. But in fact, these apostrophes are important, I think, because in our case, what I mean with FDR1 is actually just the relation between the moments. While, as you have seen in previous talks, strictly speaking, also in Kuber's book, it's really defined by the correlation function. And I think that makes a difference. I think for non-trivial dynamics, anomalous dynamics like that, it's not necessarily trivial that from the that you have the Kuber relation, and that from the more general fluctuation dissipation relation 1, it follows that you have the relation between the moments. I think you have to be very careful here because you may not be in a steady state, so there are some subtleties here. So I think that makes a difference to what you have discussed in your talk. But we can discuss, but I think it's a subtle point. So, but here, if I want to check fluctuation relations, that's all what matters here. Since we have Gaussian processes, if you know that the first moment is equal to the second moment, then you're done. But again, this is a special form, boiled down version of fluctuation dissipation relation 1. Okay, once you have that, as I've just mentioned, since the PDFs are Gaussian, then you know that you have the transient fluctuation relation. That means for correlated internal Gaussian noise, we have the transient fluctuation relation. So nothing special going on. More interesting is the second case, namely external noise. And now, in fact, the point is that we break the fluctuation dissipation relation 2 and consider what's going on. So we have no FDR2. That means we model that by this generalized Langevin equation without assuming that we have a balance between the friction on the left-hand side and the forcing. Okay. So in fact, we correlate the noise, as you see here. We assume that the correlation function of the noise is a power law, at least for long enough times. How it behaves for short times, we don't care. It doesn't matter because we're only interested in a long time limit. And we break FDR2 because we do not assume here that the friction is correlated the same way. So we have an externally driven system. And we consider two different types of correlations. Persistent ones where we just have positive decay, again with the power law here, or anti-persistent ones where you see the correlations become negative and then go to 0 from below. In this case, if you check, you find that the current is equal to a force times is linear in time. However, the variance you have to calculate, but it's easy to see that all what you have to do is you have to solve this integral for the given g, and then you have the spreading. And now there come two slides with just results. So in fact, what you find in this case is a whole slew of different fluctuation relations. So first, for persistent noise, meaning decay goes to 0 from top. If we check what we may call the fluctuation ratio, here the logarithm is just of the probability densities. We have, depending on the exponent of the power law, we have super diffusion in this case. And if you plug everything into the fluctuation ratio here, you find that you have a time-dependent prefactor here. So you see you get a deviation from the standard form. For beta equal to 1, in fact, we have a logarithmic correction here for weak super diffusion, and that shows up in the fluctuation ratio. And for larger beta, we have, in fact, normal diffusion. But still, we have a slight correction here in the fluctuation ratio. So we have a prefactor which is not equal to 1. So it's the diffusion coefficient here. So many different forms depending on the details of the dynamics. Likewise, now for the anti-persistent case, now if you consider the anti-persistent noise, in fact, one can show that if this integral is larger than 0 over the correlation function, we have normal diffusion with a generalized transient fluctuation relation, meaning with a prefactor that is not equal to 1. What remains to be studied is the pure anti-persistent case, where the integral over the correlation function is equal to 0. And again, here you get different forms depending on the value of the exponent. So in fact, this regime where beta is between 0 and 1 does not exist. And in fact, Alexei made us aware of that because there is a theorem that tells you that the spectral density of the stochastic process must be greater than 0. In this case, it's less than 0. And for that reason, this is not a well-defined stochastic process. So you need an expert like Alexei Strechkin here to spot that problem. But for beta larger than 1, the stochastic process is well-defined. In this case, we get subdiffusion. Again, with this correction of the transient fluctuation relation, you see that in a way the slope of the fluctuation ratio increases with time. Again, you have a logarithmic correction at beta equal to 2 here in the denominator. And for beta larger than 2, in fact, that's a kind of strange process because the mean squared displacement goes to a constant. We have a kind of localization. And we have an anomalous transient fluctuation relation where the slope is linear in time. So all kinds of details, but you see, for this kind of correlated anomalous dynamics, the point is that you don't get the standard form. You get deviations from the standard form, which I call normal transient fluctuation relation, where you have time-dependent prefactors, which is due to the fact that the system FDR2 is broken, so it's externally driven, which nicely connects to your talk.
Another aspect is the anomaly. I mean, it's not the anomalous factors creates different prefactors, but even in the Markov case, it's already broken the TF.
Yeah. This is a stronger case, so I would say that here the anomalies show up in the time dependence.
Even without it.
Indeed, yeah. 2 weeks ago, I heard at another conference talk by Udo Seifert, and I think he considers these cases. But so in any case, that's what you get for this anomalous dynamics, and that's what you can do explicitly. So in our case, we have this relation between the fluctuation dissipation relations and the normal one. And again, FDR1 is here defined, as I've pointed out before, as the relation between the moments. So FDR2 obviously implies this way that you have FDR1 and that you have the normal one, which means it straightforwardly follows this relation. But that means if you don't have the normal fluctuation relation, then you can conclude that you don't have FDR2. You can even check that in experiments. So this relation is important here, this implication, and that you have this relation, at least for our systems and for our definition of FDR, we have these crosslinks between FDR and fluctuation relation. Okay, relations to experiments. Now, what people usually do in experiments is they plot the fluctuation ratio, so the logarithm of this fraction, and then if you get simply a line, linear in W, here the work, then you're happy if this line has slope 1, then you have the normal fluctuation relation. But as you have seen before, in our case, we may get all kinds of time dependencies here as a prefactor. So the slope might change. And in fact, exactly this has been observed in quite some computer simulations recently. I just show one result that was published earlier this year by Crisante and Retort. What they did was they did computer simulations for, in this case, a binary Lennard-Jones mixture below the glass transition, and then just plotted this fluctuation ratio here on the y-axis as a function of the entropy production for different times. And you see if you increase the time, the slope increases by approaching slope 1. And interestingly, you see that here, indeed, for longer times, it does approach the slope 1 for small entropy production, but for larger ones, you have deviations. But for my point, most important is that you see that the slope here depends on time. And in fact, they've checked 2 other systems, 2 spin systems, and then they say in their paper even further systems and have observed similar behavior. In all cases, it seems that the slope increases with time. However, then there's another paper by Mauro Celito, earlier one even, and he has checked glassy lattice gas in a constant external field, and has actually observed both in simulations that the slope decreases and increases depending on the field strength. So something, and that was also glassy system, so it seems that something is going on in glassy systems which is very similar to what we find for the generalized Langevin dynamics. However, the precise relation in terms of a modeling is totally unclear, it seems, at least to us. So it's not clear to which extent the Langevin equations should model these systems that have been studied in computer simulations. That's a very open question. I can only say there's analogous behavior. Now, finally, example 2, real experiment, in fact, something we are busy with by ourselves. We, in fact, study cell migration. So what you can do is you isolate a single cell out of a biological organism, put it on a substrate, and then typically the cell crawls. And you can record the trajectory of the crawling cell by a video camera, as you can see here. And you define the center of the cell suitably at different times and plot the points, and then you get this trajectory of a moving cell. And I like this very much because if you forget about this cell, it's like a trajectory of a Brownian particle in a fluid. So you may ask the question, what kind of stochastic process is that? And in fact, we have answered this question in equilibrium in this paper some years ago. In fact, the cell exhibits anomalous diffusion, super diffusion for long enough time scales, but the dynamics is very complicated on different time scales. However, our point is that now, in fact, we study the cell migration in non-equilibrium, meaning our colleagues have applied a chemical gradient such that the cells crawl along the chemical gradient. And here you see the trajectories of an ensemble of cells which crawl along the chemotactic gradient. And now you can do the same thing as before. You extract the fluctuation ratio for the cells, you plot it, and in fact there are quite some subtleties here which I sweep under the rug, but if you do a proper analysis, if you are careful enough, then if you plot the fluctuation ratio at different times, in fact you can see that the slope decreases with time for the cells. Here are the red ones, and the longer you wait, the smaller the slope, similar to what we have obtained in one of the models that you have seen before. And in fact, that's what we are currently busy with to establish the crosslinks. But what you can see experimentally is we have a linear drift in the direction of the gradient first moment proportional to t. We have still super diffusion. So the mean square displacement goes to t to the beta, where beta is larger than 1, about 1.4 in the long time limit, meaning clearly you don't have the fluctuation dissipation relation of the first kind. And in fact, we can, to quite some extent, derive these results and model the experimental data by a generalized Langevin equation with external noise, similar to what you have seen before. But again, there are some subtleties that we need to deal with. Okay, that's it basically. So as a summary, we have tested the transient fluctuation relation for 2 generic cases of correlated Gaussian stochastic dynamics. Internal noise defined by the existence of FDR2. And from that, it trivially follows that you have the normal work transient fluctuation relation. However, if you have external noise, if you break FDR2, then you get deviations from the normal form. And the precise details depend on whether you have persistent or anti-persistent noise, but then you get typically time-dependent prefactors. And the point I wanted to make is that these generalized forms, as far as I can tell, appear to be important for glassy aging dynamics, which is very complicated. You have long-range correlations in time. You have aging properties. You may not have a well-defined invariant measure, all kinds of things going on. And then it's perhaps not too much a surprise that you see this in fluctuation relations as well. And indeed, this seems to be confirmed by computer simulations on glassy systems and also our experiments on cell migration. In fact, it's known that to some extent the cell exhibits kind of glassy dynamics. So it fits into this general framework. So what I told you about is essentially here contained in this first short paper that we published last year. In this paper, in fact, we study other further anomalous stochastic processes and check for fluctuation relations. And I thought that these 2 books might also be of interest perhaps to some of you. And at least now, when I did this talk, I realized that indeed these are quite different scales. So at least here you see again part of the Earth. And these are the trajectories of airplanes, while this scale is quite different. But this static framework seems to apply to many different scales. I would be happy to learn more about applications to this scale. Thanks a lot.
Thank you so much. Questions, remarks? Yes, Matteo.
Hi, I was wondering whether these transient, I have no experience with transient fluctuations. I just wonder, do you think they can be asked in terms of large deviations results?
Sure. Yeah, that's well known that there's an intimate connection to a large deviation theory. My colleague Hugo Touchette has written a very nice review about that. Indeed. So typically one is interested in the functional form in the long time limit and actually for the wings of the distributions, and then it's exactly the large deviation form. Yeah, that's known.
Can you go back to your detailed balance slide at the very beginning?
Okay.
No, next one. Next one. Okay. So, you know, this is just amusing because it reminds me of the way that many colleagues think about global warming. Think of the rho as being, you know, global temperature, global surface air temperature average, and it moving to the right towards higher temperatures and with more extreme events. So you don't know how relevant you are.
Okay. Well, this slide is all maybe just a remark that is still has to be made, that if one speaks about fluctuation relations as extensions or generalization of the second law, one should not forget that the second law is not speaking about averages. You see, the statement there is about an average thing, which is a very weak statement. The second law, as it is understood thermodynamically, is about typical behavior, not at all about averages. So in that way, this fluctuation relations is not at all extending the second law.
But there was quite some discussion also about second law violations and so on. So there are different interpretations of the meaning of fluctuation relations, but we don't want to go into this.
Okay. If not, there is tea, and I think we come back soon enough for the talk by Van Este at 355.
Okay.
Yeah. So,